Hey guys, well today we're going to be learning a little bit more about bonding. Now we've already gone through the basics of bonding. In the next couple of days are devoted to learning about the properties, the physical properties of substances that have different types of bonds, because there's some consistency there. For ionic bonds, we see certain properties. For polar covalent bonds, we see certain properties, and so we want to gather some information today so that we have a better understanding of what properties to expect. And then next class, you'll use that information to try to determine what kind of substances, unknown substances you have based on their properties and their bond types in a list of potential options. So what you should have done already is gone through this guide to testing substances to determine bond type. You'll need to know how to use all of these tools in order to test the different properties of materials. And then you should also have out this chemical bonding lab. So our goal for the next part of class, as I walk you through some of these tests, is to get information about the different properties here. After we're done doing the properties part, you guys will complete this part, plot your potential, your different substances here on the bonding chart that's a couple pages beyond this page, and then you'll use that to write down the bond type. Lastly, we'll use that information and complete this chart, which is kind of an overview of the different properties we see of the different types of bonds. Pay close attention to how we test these things, because you will be given a station on this unit exam that you will need to test the properties of an unknown substance, list those properties, and then determine what substance you think it is based on the bond type. So let's get started. The first thing that we want to observe about a substance, and we're going to start with a common substance, sodium chloride here, is the physical state. And that's fairly obvious. Is it a solid, a liquid, or a gas at room temperature? So you can see here I've got some sodium chloride, all right, and it's definitely a solid at room temperature. The next test that we want to do is malleability. And so if you think of malleability like a mallet or a hammer, we're actually going to use a hammer to test this. You don't necessarily need a hammer, but it's helpful for some substances. What we want to do with this is tap on it. And so I'm going to take just a small chunk here, and I'm going to tap on it. And we wanted to see here, does it crumble? Does it crumble, or does it change shape but stay together? So kind of think of it, does it break or does it bend? And in this case, salt is definitely breaks, and so it is not malleable. Substances that are malleable will bend or change shape but stay together. So for malleability, sodium chloride is definitely not malleable. The next thing we want to test is in a bulk sample, does it conduct electricity? Now to test this, you're going to use a small device that hopefully many of you have seen before. This is called a multimeter. Sometimes it's called a voltmeter, and there's many different versions of these. You can get all different kinds from different hardware stores and whatnot. So for this simple one, we're just going to turn it on to So we want to turn it on to the AC voltage here, or DC voltage. It really doesn't matter much on these. And it should, when we leave it be, it should zero out or be close to zero here. Now, what I want to do is, this is going to send a small electrical current through the material it's going to try. You can see if I put the tips of this together, it changes a little bit. We want to take those tips, and we want to touch two ends of the material and see if a current is conducted. Now you'll notice when I touch this salt, the reading here for volts doesn't change. There is no current that goes through here. And so that tells us that there is no voltage going through, no electrical current passing through this. We can also look at the resistance of this material and just check and see, but you can see there's no resistance. If I put these tips together, we're going to get a register. If it registers at all, if your multimeter registers at all when you touch two different sides of the material, then it's conductive. This salt is definitely not conductive whenever it's a solid. Keep in mind the first three, or the first column 3 and column 4, malleability and conductivity, we really only test that whenever we have solid substances. If you had a liquid or a gas, you would omit those and just say Na, as you can see here, because we're not going to test that. So the next part here is solubility in water. We're going to take a small amount of our salt, and it's important whenever we check solubility that we pay attention to if it dissolves or not. That's really what we're looking at. So you can see I've just got some water here, and I'm going to put a small amount of salt in my solution here. Now I've got some big chunks, so I'm going to pause and break these up a little bit. All right, I've taken the time to dissolve this, and I have my white background, and you can see that it's all dissolved. And so if the substance you put in water forms a clear or homogeneous solution, then it is soluble in water. If when you look on the bottom, after you've swirled it and stirred it to try to get it to dissolve, if there's still a lot left on the bottom and you've only started with a small amount, then you know it's not soluble. Also, if the water gets cloudy or murky, you know it's not soluble in water because it's just kind of suspended in there and it's not translucent. So salt is definitely soluble in water. The next test we want to do is conductivity in water. Now we only do this if a substance dissolves in water. And we're going to use what's called a conductivity probe. And we're going to hook this into our computers. I'm going to show you here. I have the Vernier software hooked up to my computer. And so you'll have to be able to read this. The conductivity part here, is in microsiemens. And that's a unit that you won't necessarily need to know. But it is the measurement that we'll be using here. Sorry, I lost it there. So that's in microsiemens per centimeter for conductivity. So what we're really testing here is when we try to pass a current through the solution, that's the substance dissolved in water, does it conduct? So I'm going to go ahead and show you the procedure you want to use, and you need to follow this procedure. The first thing we want to do is to make sure we don't have any contaminants on our probe. We're going to rinse it off with deionized water. So we just take our rinse container and just do a nice quick rinse to make sure there's nothing on there. Okay, now I'll set that aside, and I'm going to put my probe into the solution here. But I want to show you right now the conductivity is 11, and I'm going to set this in here, and you'll see the conductivity goes up to over 4,000. So that's a highly conductive solution, meaning a current is easily passing through between the two parts of the probe here when it tries to send a current through. Usually that tells us that there's ions in the water, and that usually only forms when we have an ionic substance. So you'll see that as we move forward here. Okay, so that solution is conductive in water. One thing you need to do is make sure on your conductivity probe that whenever you're working with that it's set to 2,000 as your base unit and not 200 or 20,000. So it should be switched all the way to the bottom on that 2,000 mark. Another thing to note, if I take some pure water here, let me just show you, and I rinse my probe off again with deionized, so because there's a little bit of salt water left on there, and I stick it into my deionized water here. Okay, the conductivity registers that it's slightly conductive, and that's just because there's a few contaminants in the water. That's not really showing conductive. So this would be a good thing to write down on your sheet. If the conductivity is less than 200, then we're going to call that not conductive, and we probably just have a few contaminants in the solution. If it's above 500 or 1,000, that's a conductive solution. So that's a good note to make on your guide sheet that you already read. Okay, let's move on. Those are really all of the tests that you need to do for this substance. And so we saw that salt is not malleable, it's not conductive in bulk state, it is soluble in water, and it does conduct whenever it's in solution. And so then in a minute here, you guys will fill out the rest of this. plot your average and difference on the ionic bonding triangle on the next page there, and then determine where does this bond type fall. And you can already predict what kind of bond it is, and you'll see that in just a minute. So let's move on to our another substance here. I'm going to jump down to copper. And the Cu with the little X on the bottom simply means that we have copper, lots of copper atoms all bonded together. So I have a couple of samples of copper here that we can work with. All right, in the first test, we're just going to look and see is it solid, liquid, or gas. Of course, copper is a solid at room temperature, and so we're going to write solid there. The next one is malleability. So whenever we take a hammer to copper, and you don't actually need a hammer, you can just see it bends easily, and so this is a malleable substance. But if I do hammer it a little bit, okay, we can see it doesn't break. It changes shape and bends. So copper is definitely a malleable substance. You can hammer it into sheets or shapes or pull it into long wires, and it bends, it doesn't break. Copper is malleable. All right, next one, solubility in water. So let me take my water here. I've put some water in there, and as you might guess, copper doesn't dissolve in water, so it is not soluble in water. Now, because it doesn't dissolve, the next column, conductivity in water, that is not going to be applicable, meaning we're not even going to test it. The only time we test solubility, conductivity of a solution is if it forms a solution. If it doesn't dissolve, then it doesn't form a solution. Okay, I accidentally skipped one here, and that's conductivity of the bulk sample, which is the conductivity in the solid state. So let's come back to our multimeter here to test that. And again, I'm going to set it, you can do resistance here, and that's fine. It should register as well. So I'm just going to touch my probe to two different parts, and you'll notice, right, that we get a change. So this is definitely conducting electrons through this piece of copper, so it is conductive in the bulk state. Again, if you see nothing, if there's no register of any kind whenever you touch the two ends, then it's not conductive in the bulk state. So that's copper. Copper is a solid at room temperature. It's malleable. It's conductive in the bulk state. It's not soluble in water, and we wouldn't test the conductivity in solution. Let's look at another one here. So the one below copper is C3H8OH, which is a type of alcohol. And the type doesn't matter a whole lot. There are lots of different types: methyl alcohol, ethyl alcohol, propanol, and various others. And so let me get our sample here. I'm just using an isopropyl alcohol, which is purchased at the grocery store. And this is actually dissolved in water already. You can tell because it says it's 91%, and that means the rest is water. So it's mostly alcohol, but there's a little bit of water in there. Now for our phase at room temperature, of course, this is going to be liquid. And for malleability, we're not going to test that because we only test malleability for solids. So you're going to write NA or not applicable for malleability. Same thing with conductivity of bulk state. We're not going to test the conductivity of this substance because it's not a solid. So we are going to test to see if it is conductive in solution. Now, how do we know if it's soluble in water? What we want to do is actually put some water in here with it and see if the water separates from the solution or it dissolves in. So when you do this, you can see that, again, it forms a homogeneous solution. If it got cloudy or you could see a separation, like with oil and water, then you would know that it's not soluble in water. So this alcohol is soluble in water. And the last thing we want to do is test the conductivity to see if it conducts. So we get our conductivity probe again. We're going to do a quick rinse. Always very important to rinse first. All right. And coming back over to our readings, right now I'm at 11. And when I put my probe in, right, we're going to see that the conductivity didn't change at all. So alcohol is not conductive whenever it's in solution. So that's all of the tests we need to do for our alcohol. Again, you'll plot out the place on the bonding triangle. And you should see, once you plot this out, go ahead and write this down, that alcohol is a polar covalent bond. We want to look at the carbon-oxygen bond. That's where the polarity comes from in this molecule. So go ahead and write polar covalent for that carbon-oxygen bond. Now we'll move back up to water. Hopefully from all of your knowledge of water you can just fill this out. We know that water is of course a liquid at room temperature. We wouldn't test the malleability. The conductivity of the bulk sample we're not going to test. Is water soluble in water? That's kind of a silly question, but does it make a homogeneous solution when you mix it with water? Yes, it does. So we put Na there, but technically it is soluble in itself, which all substances are soluble in themselves. Conductivity in water. When we test this, if we have pure water, so let me get some again. Water, we'll rinse. Okay, my conductivity is still at 11, it hasn't changed, and I'm going to put some deionized water in here. We always want to use deionized water so that it doesn't have any ions to change the conductivity. So basically you're working with pure water, or fairly pure water. Rinse, and we're going to put this in, and again, my conductivity is still 11. So water is not conductive in solution. You may think, well, you can get electrocuted, right? If you touch water, you put your toaster in the bathtub, which I don't know why you would make toast in the bathtub. But the reason for that is we have lots of ions and other things on our skin that dissolve into the water and make it conductive. For example, salt is on the outside of your skin, whether you notice it or not. And so if you get into a source of water, it's pretty likely that you're going to dissolve some of those salts into the water, making it conductive. But pure water is not conductive. Okay, let's move on to the next one, silicon dioxide, or SiO2. This one is actually a bit of an anomaly, so we'll walk through this one together. This is called quartz, or silicon dioxide. And so it's a very hard substance. If we test the malleability, you can see it's a solid at room temperature. If we test the malleability, you can see it breaks. It's brittle. And so this substance is not malleable. Okay. Now the next thing we'll do is check the conductivity of the bulk sample. So we're going to take our multimeter. We're going to put the probes on two different sides, and we get no register. And let me put these together just to make sure it's working. Yep. Okay. Touch it in two different places. Lots of different places. Nothing's happening. So this is definitely, quartz is not conductive in the bulk state. The next one would be solubility in water. So if I take this and I place it in water, right, and I try to dissolve it, I could sit here all day and try to dissolve it. It's not going to dissolve. So silicon dioxide, or quartz, is not soluble in water. Now, because it's not soluble, it doesn't dissolve into and make a solution. We're not going to test the conductivity, so we're just going to say Na for conductivity in solution here. Okay. The last one that we can test out here is the mineral oil. And so the focus there is going to be the carbon-carbon bond. Mineral oils, long chains of carbons. And so I have some mineral oil here. And we're going to go ahead and take a small amount of this out. Okay, it's kind of a viscous, thick liquid here. So you can see that at room temperature, it's definitely a liquid phase of matter. Okay, we won't check the malleability because it's not a solid; it's a liquid. And we won't test the conductivity of the bulk sample because it's a liquid. We do want to test to see if it's soluble in water. So now we can go ahead and add some water to this. And what I can see happening, and might be hard for you to see, is there is a layer, two different layers forming on this. And you definitely aren't going to be able to see it very well in this. If it was colored, we'd be able to see a little bit better. But it is separating into two different layers, a water layer aqueous and the oil layer. So because these are not miscible, meaning they won't form a homogeneous solution together, they separate, the mineral oil is not soluble in water. Lastly, we can test the conductivity of that solution. We can just see if it conducts electricity or not. And so I can take that sample here and see, whenever we test it, if the conductivity changes. And I will tell you, it does slightly change. So it went up to 27 from 11. But again, that's way below our threshold. And so this is definitely this is not conductive in solution. And one thing you'll notice, it's very hard to clean this probe off now. That's because this is an oily substance, and you start to see the bubbles forming where they're separating there too. Those are just water bubbles. And so this is, again, just to show you that it's not soluble in water. Okay. So we've gone through all the different types of tests. You do need to know how to do these, and you will do them in the lab next time. The next part of this is for all of your substances here, for each of the types of bonds that are indicated. You want to go ahead and determine the electronegativity of each element, and it doesn't matter which one is which here. You want to determine the change in or difference in electronegativity by subtracting them, and then the average electronegativity here. You'll then come and plot on your bonding triangle the location of each one of those substances. Keep in mind, I should have drawn in here around 0.4, you should have drawn kind of a fuzzy line between polar covalent and, this is nonpolar covalent and polar covalent. And as we get farther and farther up, we get more and more polar bonds there. So if something is in this area, it's more on the nonpolar side. And if it's in this area, it's more on the polar side of the triangle. So plot each one of those out. Obviously the ones on the bottom 4 or 5 here, those are already done for you. But you want to use that bonding triangle, this information in the bonding triangle, to then list the bond type for each one of those. Once you've done that, the last part of this is then compiling your information. So what you want to do is look at all of your ionic bonds and then determine what was the general physical state for ionic. You'll notice that all ionic substances are solid at room temperature. Then look at malleability. Were any of the ionic substances malleable? Then look at conductivity. So you're basically using all the information that you've gathered here and focus on the specific bond type we're talking about and determine properties here. Obviously, if something is not applicable, you should write that. One thing that I do want to point out is we said that quartz, the SiO2, was a polar covalent bond. But this is a bit of an anomaly because we have some covalent bonds that form what we call as a network covalent solid. And they do some cross bonding. And that makes them much more likely to be a very hard, durable solid that won't dissolve at all. So when you're filling this chart out, you may want to write a note that there are some exceptions to some of these. For example, polar covalent bonds can be found in all phases, but usually they're softer. And usually they dissolve in water, but this does not. So there are some exceptions. The same thing with ionic. Most ionic compounds dissolve in water. They're soluble in water, but there are some that do not dissolve in water. There's a good amount that are not soluble in water. So take a little bit of time to complete this chart, and you'll use this next time whenever we look at our unknowns. You'll be given multiple unknown substances. You'll have to test their properties and determine which substance you think you're working with based on the given substances here. That's all for now.